All right, so here we are, made it to Unit 4. This is it, the top of the hill. It's all downhill from here. Get through this long one, and then Unit 5 is nothing. Okay, so right at the end of Unit 3, I quickly mentioned the null hypothesis. So we're going to get a little bit more in depth about the null hypothesis. And the null hypothesis, right? Basically states there's no different, if we study a population, and let's remember population versus the sample, right? If we study the entire population, there is not a difference between the means. So if I studied every boy and every girl in a school, or however I define my population, let's say I studied every boy and in the group and every girl in the group, all the Delta College students. So all the boys in one group, all the girls in another group. And I got a difference in their reading, the means of their reading scores. It's only because that wouldn't happen if I studied the entire population. The reason we get differences in the means according to the null hypothesis is sampling error, because we're not studying entire populations. Hope that makes sense, right? So the null hypothesis states there is no difference between the means. Right? So no matter what, it would always balance out, right? And anytime there is, it's due to sampling error. Keywords. Null hypothesis and sampling errors, right? Keywords. So, the difference between the means in any population study is 0. That's basically what the null hypothesis says. Our goal as researchers is to prove the null hypothesis wrong, typically, is what we're trying to do. All right? So, there's no real mathematical formula, but this is how we would state the null hypothesis using mathematical type language, right? But it's not a formula. So the null hypothesis states, right? So the null hypothesis states the difference between mean 1 and mean 2 is 0. There is no difference, right? So this is the mean for one group, and this is the mean for the other group. I know we only use this because, like I said, it's not a formula, so we don't use M like we would in our algebraic expressions, right? So that's what that says, right? There's no true difference between the means. However, our job is often to prove that there is. Right, that's what we're looking for. So we have an alternative hypothesis. Whatever my research study is, whatever my research question is, like say, go back to the simple ones, men like coffee more than women. That's my alternate hypothesis, right? So I'm saying that there is a difference between the means, and men like coffee more than women. So then I would represent that in this way. So now what I'm saying is my alternate hypothesis is right. Mean 1 is greater than mean 2. And that's my alternative hypothesis. Now, this is also what we call a directional hypothesis, because I'm actually saying one is going to be greater than the other, right? So I am making a definitive statement. There's also a non-directional hypothesis, which just says, I'm just saying there's going to be a difference, but I'm not going to go out on the limb and say which one is going to be bigger or smaller, right? Okay? So, in which case that is my alternate, oh, never mind. I'll wait till I turn it. So in that case, all I'm willing to say is my alternate hypothesis says mean 1 just will not equal mean 2, right? Whereas the null hypothesis basically says mean 1 will equal mean 2. All right, so that's our null hypothesis. There's no difference between the means. Let's see. I'm not going to go into that. All right. So now the question is, we have to make decisions about the null hypothesis, right? So how do we, as researchers, how do I go about showing that my data is valid to say that I can say the null hypothesis is true or not true? And actually what we say is we reject the null hypothesis, or we don't reject the null hypothesis based on statistical significances, which is what we're going to start talking about this unit, right? So, we work on the, I'm guessing maybe you've heard the term probability before. So really what we come up with is the probability that the null hypothesis is true or not true. The probability is going to say whether I reject the null hypothesis or fail to reject the null hypothesis. That's the proper language, right? So we're going to talk about probability. And, give me a second here, another key word. And what I want is, I run tests, right? So I test and I come up with the probability of the null hypothesis being true, right? So, and the probability is small p. That's how you're going to see it defined. That's how we're going to do it, right? So, basically, what we want to see is, I guess that looks too much like a capital P. So you might have seen this hopefully before in some articles you read or some textbooks or something, right? You see the notation like this. And what this means is the probability is less than 5 in 100 that the null hypothesis is true. The probability of whatever statement I said being true is less than 5 in 100, right? And this is the minimum value where we're going to reject the null hypothesis. So let's make that, right? 5 out of 100 is the best. You're also going to see notations, and we'll just do this again, where P, the probability is 1 in 100 that I will be wrong. 1 in 1,000 that I will be wrong. And we'll show how to statistically get these numbers to validate our statements, right? Okay. Well, this is what we do, and this is demonstrating statistical significance. My data has statistical significance when I can make these statements, and that's how that works, right? So, and we're going to spend a whole lot of time right now on how we go about proving this or disproving this or how we get these numbers, right? So, the other thing about the null hypothesis, right, is there are 2 errors possible, right? So there's a type 1 error, is when I've rejected the null hypothesis, but it's actually true. And I'm just going to start writing NH so I can stop to write this, right? So I rejected the null hypothesis when it is true. And the type 2 error. I failed the only other side of the coin, right? I failed to reject the null hypothesis when in fact it was not true. And there was a difference between the means, okay? So remember what I said, so if you were to see this, that's what I want to say.
Don't we usually only use 0.05 though?
Yeah, that's what I'm saying. If you were to see this, you would know it would be a mistake. I just want you to know, right? 0.05 is the minimum value.
And that's like what we usually
Yeah.
go off of.
Well, that's what you usually find because, of course, getting statistical significance down to 1 out of 100 is much more challenging. However, it does happen, and of course, 1 out of 1,000, right, gives me that much more confidence to reject the null hypothesis, but it's also that much harder to get. So. And then we're not going to see this again, but you may see this someplace else. This is an alpha, and this is beta. We're not going to use that again in this class, though, so you don't have to worry. All right? All right, so those are our decisions about the null hypothesis. That's how we keep working. All right, so of course, like I said, we have to be able to prove all this and get those numbers, right? You know, just like be able to say, oh, it's statistically significant or not. So how do we go about doing that is the question, right? And so let's just say, so there's 2 ways we go about, right? Remember, so we can do a survey, right? Or we can do an experiment. Either way, it doesn't matter. Either way, whichever way we choose, typically for us researchers, we're going to be doing surveys. But either way, it doesn't matter. Whether the results were obtained from a survey or an experiment, it's still the same issue, right? So, what we use to get some statistical significance is the t-test. The t-test is what we're going to learn about to do this. However, let's just start talking first, right? So, the null hypothesis, right, part of that states that the only reason there's a difference between the means is because of sampling error, right? So, you have to understand there's some things about sampling. Unfortunately, there's no formula that says what the right number of people are, what the right this is, like how to pick your sample, but there are guidelines, and we'll go through some of them before. But here's some typical, here's a couple of quick things, right? So, 1, the larger the sample, the larger the difference between the 2 means. So the larger the differences between the 2 means, the better off you are. And when I say the better, it just means it's less likely sampling error, right? That's all I'm saying. And then 3 is less variance less variance between your subjects. And we're gonna start talking about this, what is dependent data versus independent data. And I may have mentioned this before, I never know. But, you know, when we do research and studies, like Sweden is the best place. And don't ask me why, but they have an inordinate number of twins born there. And so they have been doing research and doing studies on sets of twins forever. And they have some longitudinal studies that go the lifespan of people, of a set of twins, right? Because that's your best match subjects. Like I got the same DNA. Identical twins, of course, are perfect. Fraternal twins are the next step. Siblings are the next best. And you work your way down. And that is what we call dependent data. Most of the time, however, though, especially in a survey, we get what is known as independent data, where the people have no relationship whatsoever in the sample. So, we're going to go over that again. You don't have to worry about it. But it's going to come up because there's two types of t-tests. Right? There's one for independent data. And then there's one, of course, for dependent data. This is also referred to as a two-tailed and a one-tailed. Okay? So, we'll see that too. So, of course, what the deal is, it's really important that you select the right test and you understand who your subjects are and who your groups are, okay? So, give me a second, I'm gonna erase all this and then we will work on the formulas because I know you guys have been dying to see another formula, right? This is a math class. I'll start with computations for the t-test with independent data. So this is, like I said, the survey that you just mailed out. You may get a brother and sister answering the survey, but that wasn't your target. Like you just used the shotgun method, and these people have no relationship typically to each other. That even includes, so even if I was to just like pick a community, those people are still independent, right? Make it clear. They're only dependent when they have some type of relationship, like I said, siblings, twins, that kind of thing.
Would like spouses count?
No. Well, they could, depending on what you research. So spouses could count depending on what your research question is, more than likely.
Okay.
Right? Anyway. So this is for independent data, people that know, they probably don't even know each other, basically. All right, and here it is. T equals mean 1 minus mean 2, where mean 1, I don't even need to do that. Stop doing it. M1 is always the larger M1 is just always the larger mean. It doesn't matter what group it belongs to. It's irrelevant, right? So M1 is just always the larger mean because we want to have a positive number outcome. Okay? All right, so that's really easy, right? M1 minus M2 over SDM, which is the standard deviation of the mean difference of the means, the difference between the means, right? So this is the standard, I'm sorry, I keep saying standard deviation, the standard error for the difference between the means, right? So this is, of course, the challenging piece. Life would be no fun if everything was as simple as that. So here we go, right? So N1, so here we go. N1 is number in group 1, right? Of course, then N2 is number group 2. Make this simple. S1 is the standard deviation for group 1. All right. And so, so here we go, right? N1, N2, S1, S2. That's all you need for this. You probably already figured it out from doing something else along the way, right? But for us tonight, we're just going to give it to you to make it easy. So, Alright, so here we go. Group 1, the median is 24, the standard deviation is 1.5, N is 12, and for group 2, mean 2 is 22, the standard deviation is 1.4, and N is equal to 11. Once you have all that, we just do what we've been doing all along, right? Nothing to panic. It looks like a mess, and you know, they are getting more complex, but it's still the same basic stuff, okay? So as we plug in the numbers, we're going to go to 12 minus 1, right? Times 1.500. And actually, let me not do it that way. I don't want to confuse you.
Also, fix your twos. Oh my God.
Huh?
Fix your twos.
Fix my tunes? Okay.
That doesn't even look like a number.
Well, the pen's so thick, it's kind of hard. It's a good thing I got a camera crew here to keep me in line.
Yeah, kids are gonna be
All
confused.
right, so here we are, right? Over 12 plus 11 minus 2, right? 12 plus 11 minus 2. And all of this times 1 over 12 plus 1 over 11. Okay? Which is equal to the square root. And please, I can't say enough, don't drop the square root sign in the middle of your formulas. People do it all the time. 7 times plus n minus 1 for 2, right? N2 minus 1 is 10 times 1.960. All right? All over 21. All right, 12 plus 11 minus 2 is 21. All right. I am going to have to move away. I'm going to stay here as long as I can. Now, we're at 24.75. All right, and all of this is a problem in your book. It's on Canvas. You can follow. You can review it again later. Okay. So then finally we have All right, so I didn't do anything fancy here, I just did the same multiplication. You can follow it along in Canvas when you need to, if you want to review it. This is it, and then of course for all right, so sorry about the jump from the classroom to here, but it was the quickest fix I could do. So this will be cut in to Unit 4, hopefully by tomorrow or Saturday at the latest. So I got to the end of computing SDM, and that right? So that was equal to 6.606. And that's what I said was the observed value, but that is not true, right? We need to then complete the t-test. All right, so M1 minus M2 over SDM. And that in this case becomes 24, right? Minus 22 over 0.606. Is equal to 2 over 0.606, which is actually equal to 3.300. All right, so this is our observed value. This is what happens when I don't have somebody in the classroom with me to help me point out my mistakes. So here is our observed value for the t-test, right? And then the degree of freedom is equal to n1 plus n2 minus 2. In our case is 12 plus 11 minus 2, or 21. All right, and so we go to the table, right? We look up the degree of freedom for, so now for the t-test, we go to table 4, right? And if you go down to 21, to go into the first column for degrees of freedom for 21, you find out the critical value at 0.05 equal to 2.080. So our observed value is greater than our critical value, and in this case, we will reject the null hypothesis. All right. So sorry about the confusion. We're all like everybody else, we're still trying to get this right. So hopefully this will be cut in, and you will find it differently, right? All right. So in this case, we can also see that at the 0.01 level, all right, the critical value at the 0.01 level is actually 2.831. And so our critical value, so actually C at the 0.01 level, right? But not the 0.001 level, okay? So this is what we do, right? So this data has statistical significance. Right? And we reject null hypothesis. So once again, sorry for the thing. Here's the deal. It's also in section 38 in the book, okay? So this is about reporting your t-test, right? And your statistical significance, this is how you say it, right? So you can put a table together that will show the means and the standard deviation in n and all the figures that you use to do your computations, right? That's basically the numbers we had listed over here a minute ago. Now we just put them in our favorite format, the table. And then this is the kind of sentence you write, right? So the difference between the means is statistically significant. And then in the parentheses, you would put the values. T was equal to 3.22. There was a degree of freedom of 10. P was less than 0.01. So we were very confident about it, right? And we used the two-tailed test. So from this, people would know what table to go look at. They would go look at a two-tailed test if they wanted to check your data, and they would look up the critical value and compare it to your observed value. That if they really wanted to do it, that's what they would do. But what you're telling them here is you were thorough and you followed through, and this is where the information is if they want to see it. You can also say the difference between the means is statistically significant at the 0.01 level, and then in your parentheses you would leave that part out, and you would just put the value of t, the value of your degree of freedom, and the test that you used, the two-tailed test. Another way is the null hypothesis was rejected at the 0.01 level, right? And then in your parentheses, the same thing, the value, the degrees of freedom, and the test that you used. Now, this shows statistical significance. This is how we say it, right? But let's talk for a second about something that we're just going to talk about for a minute. This shows statistical significance. Oh, I want to point out, in your book, if you're following along, the second sentence does not state statistically significant. It just says the mean is significant. The difference between the means is significant. My recommendation, you always use the adjective statistically in front of significance. I don't know. It's just the way I was taught. In the book it says something else, but I would always use statistically significant rather than just significant. Okay? I'm not going to ding it for it, though, if it happens to come up on a test. Don't worry. All right? So, there's also, so let's say I've studied something. I've studied the use of Zoom as a tool for distance education. And it turns out distance education is much more effective than in-class education. I'm hoping that's not true, but I'm hoping at some level it is. And at any rate, this is what I said. Statistically, I've proven before we had to go on, everybody went district education. This would have been an example. So I say that it's statistically significant. I can show that Zoom is more effective than in-person learning. However, at the time, and even now, it's not practical significance. It's really not working for a lot of people because they don't, how does the school district or how does the parents or whoever buy all the equipment necessary for children to learn online? How do we get to teach them how to use the equipment? So there's all kinds of barriers which we are experiencing right now. See, I used to use this example anyway, so it's kind of funny. But at any rate, right, so there's practical significance that my study really wasn't even probably worth doing because putting the plan into action is not practical. So whatever the case may be that I might studied and showed that something was more effective than the way we were doing it at the moment, if you can't implement the new practice, it has no practical significance. Versus, okay, so that's the difference between statistical and practical. Right? You want to study things that are going to have some practical significance if you're right. Okay? All right. Now let's move on to what happens when it's not statistically significant. All right, so then, of course, as unfortunately is often the case, we did some research and it proved not to have any statistical significance, in which case we have to report that too, right? Oftentimes our research doesn't pan out. That's the way it is. That's why we do research, right? To find out if something is if we're going to be able to worth something, if something is effective before we put it into practice. We do the research to try to figure that out. At any rate, it's the same sentence, only now instead of the difference between the means, it's the difference between is not statistically significant. The difference between the means is not statistically significant at the 0.01 level. Right? And the same thing, the null hypothesis was not rejected. So it's the same sentence, you just add not in the appropriate place, basically, right? Okay? Now we're going to talk about the t-test for dependent data. And remember when I talked about dependent data, I said our subjects have some kind of relationship, right? So we talked about the identical twins, fraternal twins, or just siblings. Right? Brothers and brothers are best, brothers and sisters are the next level down. But they have some kind of thing. And in which case now we're studying pairs. So we're going to pair them, right? Twin 1 and twin 2, twin 1 and twin 2, sibling 1 and sibling 2, right? We're going to put one, this is more experimental, right? This is more like an experiment. And we're going to put one in the test group and one in the control group, or one in the experimental group and one in the control group, which means basically I have a new intervention I've decided. And when I was a therapist, I decided I stumbled upon this thing and it seemed to work with a lot of clients. So now I'm going to do a study about it, and I'm going to do a controlled study about it. So I am going to get a group of siblings who magically all suffer with anxiety disorder, and my intervention is for anxiety disorder, and I'm going to put one sibling of each pair in the experimental group, and I'm going to put one sibling of each pair in the control group. The experimental group will get the new intervention, and the control group will get a standard intervention that's already in practice, right? And that's our experiment. And my goal is, my hypothesis is that the experimental group will improve on some type of anxiety scale, decreasing their anxiety more than the control group.